Welcome back. In our previous lecture, we have concluded our discussion on carrier drift phenomena. It was our first type of carrier transport phenomena. In this lecture, we will start our discussion on the second type of carrier transport phenomena, that is carrier diffusion. So before starting our formal discussion on carrier diffusion phenomena, let's get some insight about what does diffusion actually mean. Let's consider an empty tube and you have placed a membrane inside of the tube and separated the whole tube into chambers. Initially, both the chambers are empty, but now we will fill one of the chamber with some gas particles. After some time, let's say the membrane is broken. So what will happen now? Will the gas particles be confined in their original chamber in the half of the tube, or the particles will start to move and propagate throughout the tube? The answer is the particles will not be confined to their original position, and due to the random velocity of these particles, they will start moving throughout the tube, and ultimately some particles will move from one chamber to another. This process will go on until we have a similar distribution or similar concentration of these particles in both the chambers. This is the process of diffusion. So diffusion process will occur when there are some difference in concentration in the different parts of the experiment. In our case, in the case of carrier diffusion phenomena in semiconductors, if electron or hole concentration in two regions of the semiconductor is different, due to this difference in concentration, electrons or holes will flow from high concentration region to low concentration region. We will start our discussion on diffusion phenomena with a simplified analysis. Let's assume that electron concentration varies in only one dimension. In the practical case, we may have electron concentration varying in all the three dimensions, but for the sake of simplicity of our analysis, we are assuming that electron concentration will vary only on x direction. Temperature is assumed to be uniform. So let's take a look at the example we are particularly talking about. Here is a graph you can see. In the x-axis we have distance, and in the y-axis we have electron concentration. In our previous discussion, we always considered the electron concentration to be a constant value. We have used a particular value of electron concentration n in mathematical problems and elsewhere. But now we will consider a non-uniform doping. Non-uniform doping means if in the doping process the doping concentration in different regions of a semiconductor is different, then due to this non-uniform doping, electron or hole concentrations in different regions will also be different. So we are considering a similar scenario here. This is a linear function, but in the practical scenarios you may not face a function or a distribution as simple as this, but for sake of simplicity we are considering just a linear function. So what is happening here? Let's say when the distance was something like this, our electron concentration is very low. It's somewhere here. But as the distance is increasing, the electron concentration is also increasing. At some point here, at very high distance, electron concentration is also very high. So before diving into the detailed calculations, let's take a look at this graph and get some insight out of our common sense. So what is happening here? Electron concentration is low in this region and electron concentration is high in this region. Or if you consider the x-axis, electron concentration is low in this distance and electron concentration is very high in this distance. So what do you think will happen? Electron concentration is higher in this region and electron concentration is lower in this region. So we can expect that electrons will flow in the negative x direction, right? And as the current flows in the opposite direction of electron, we will have a diffusion current in the positive x direction. That is what we can get from this graph with some common sense. Now let's formally derive the equations and see if our understanding matches with the derivation. Let's go. So before deriving the equations, let's specify some parameters related to this example. The first one is L, or mean free path. So what is mean free path? Mean free path of an electron is the average distance an electron travels between collisions. So what does that mean? We know that when an electron is in a semiconductor, it's constantly moving. So an electron gets involved in collisions after some random intervals. An electron travels a distance between two collisions, and L is actually the average of all these distances between two collisions. That is what we know as mean free path. And another one is VTH, which is the mean thermal velocity at which electrons will move. So we will try to determine the net rate of electron flow. Let's say some electrons are at x equal to minus L position and some electrons are at x equal to plus L position. We are considering these two particular positions for now. The electrons are randomly moving. So we can expect that out of all the electrons in x equal to minus L position, half of the electrons will move in this direction or in the left direction, and half of the electrons will move in this direction or right direction. Again, same things happen for the electrons at x equal to plus L position. Half of the electrons in this position will move in the left direction and half of the electrons will move in the right direction. So the electrons from x equal to minus L position, which will move in the right direction, will pass the x equal to 0 plane, and in similar fashion the electrons that will move in the left direction from x equal to plus L position will pass the x equal to 0 plane. We will try to determine the net rate of electron flow through this x equal to 0 plane. First of all, let's consider the electrons coming from x equal to minus L position. At x equal to minus L position, electron concentration is n of minus L. Here you can see half of these electrons will pass in the right direction and move through the x equal to 0 plane. So we will consider half of this electron concentration, so half of n minus L. And if electrons are moving fast, then rate of electron flow will be high. If electrons are moving slowly, the rate of electron flow will be less. So we can see that rate of electron flow is directly proportional to the velocity. If the velocity is higher, rate of flow is also higher. If the velocity is lower, rate of flow is also lower. So that explains this part of the equation, half of n minus L VTH. Let me recap this once again. Why there is half of n minus L? N minus L is basically the electron concentration at x equal to minus L position, and as half of these electrons are moving in the right direction to pass this x equal to 0 plane, we will consider a half in front, and VTH is the velocity. As these electrons are moving in plus x direction, so there is a plus sign in front of it. Obviously we will not put the plus sign explicitly, but the sign is positive. Now consider in the similar fashion the electrons from x equal to plus L that will move in the left direction to pass this x equal to 0 plane. Again, at x equal to plus L, the electron concentration is n plus L, and half of these electrons will pass through this x equal to 0 plane. So we will consider half of n plus L. Similarly, we will multiply this with our thermal velocity, and this time we will put a minus in front because these electrons will be passing the x equal to 0 plane in the negative x direction. So that explains the minus sign here. VTH is obviously the same because it is the mean velocity. So we will take half VTH as common, and in the brackets we have n of minus L minus n of plus L. Just to remind you, n of minus L is the electron concentration at x equal to minus L position, and n of plus L is the electron concentration at plus L position. So let's check if we are in the right direction. We can check it. If you consider this equation, half VTH into n of minus L minus n of plus L, we will get some idea. In our previous discussion from common sense, we have argued that electrons will move in this direction because electron concentration is higher in this direction and electron concentration is lower in this direction. So we have argued that electron will move in negative x direction. Let's say if we are in the right path. Consider n of minus L and n of plus L. We can clearly see that n of plus L is greater. So this subtraction will result in some negative value, and negative value means if this Fn has a direction in opposite of this x, that means in the negative x direction. So we are aligned with what we have assumed earlier, that electrons will move in negative x direction. Okay, so let's move on. Now we will essentially expand these two functions with Taylor series. We already know the basics of Taylor series from our mathematics knowledge. I am not going to recap it here, but if you have any confusion, you can just Google about Taylor series expansion and you will get some insight out of it, how we can reach this conclusion from here and this conclusion from here. Of course, Taylor series expansion will give me infinite number of terms, but we will not consider the higher order terms and only the first two terms are considered. So n of minus L will become n of 0 minus L dn by dx, and n plus L will result in n of 0 plus L into ddx of n. So if we just carry out some simple calculations here, the n of zeros will be cancelled out and we will have 2L ddx of n. That 2 will also cancel out with this half, and the ultimate result is Fn equal to minus Vth L ddx of n. So essentially this is our net rate of electron flow, and this is well aligned with our assumption, because after all these calculations we have a minus sign in front, that is indicating that electrons will have a net flow at minus x direction as we have assumed earlier. Now we have derived the equation of net rate of electron flow. We can readily derive the value of current density from net rate of electron flow. We know that current is basically flow of charge or rate of flow of charge, Q by T. So rate of flow of charge. Fn is the rate of flow of charge carrier. Electron is the charge carrier here. So Fn is the rate of flow of charge carrier. And if one charge carrier electron has a charge of minus E, then if we multiply this whole thing with minus E, we will get the rate of flow of charge. So once again, this is our rate of flow of charge carrier electron. An electron has a charge of minus E. So current density is nothing but this term multiplied by minus E. So current density J is equal to minus E multiplied by Fn. If we put the values of Fn here, we will have plus E Vth L ddx of n. Here E is the charge of each electron, Vth is mean thermal velocity, L is the mean free path, and n here is the electron concentration, which is a function of x. If this n were a constant, I mean if the case was for uniform doping, this n would have been a constant value. So this differential will result in 0 and the J will also be 0. That means we will not get a diffusion current if there is uniform doping. We will only get a J if the doping is non-uniform and n is a function of x. So that is our derivation of current density. Now let's dig into some more detail and see what we can do with it. Let's consider this graph. This was our electron concentration, and as electron concentration is increasing in the positive x direction, the electrons will flow in the negative x direction, and our electron flux, you can see here, has an arrow sign from right to left, that means in the negative x direction. As we know that current due to electron flow is in the opposite direction of electron, that's why electron diffusion current density is in the opposite direction of electron flux. We can also prove it from the equation we have learned earlier. We have seen that Fn has a minus sign in front that indicates that electrons will be flowing in the negative x direction, but in the case of current we have a plus sign here that indicates that current will flow in the positive x direction. The diffusion current due to electrons in the x direction, that is denoted as JNX diff, this is equal to E multiplied by dN multiplied by ddx of n. So there is a new term dN here. You can see a similarity between this equation and this equation. This VTH multiplied by L is essentially dN. This dN is electron diffusion coefficient. We have already talked about mu n, which was electron drift coefficient. Similarly, the dN is another constant term for a particular semiconductor material, that is electron diffusion coefficient. Of course, this dN will vary from material to material, and also dN varies with temperature. Now let's talk about holes. If we have a similar function, but this time it is the function of hole concentration, let's see what will happen. The same function, hole concentration is lower in this region and higher in this region where distance is greater. If the hole concentration is increasing in this direction and there are high hole concentration in this region compared to this, essentially holes will flow from high concentration region to low concentration region. You can see the arrow here denoting the hole flux. Hole flux is basically the direction of the flow of holes. As the hole concentration is greater in this direction compared to this direction, holes will move in this negative x direction. That's fine. And now, as we know, holes are positively charged and the current essentially flows in the same direction as the holes will flow. That's why we are getting a hole diffusion current density in the same direction as hole flux. So previously, if we have got a plus sign, as the electron diffusion current density was in the positive x direction, now we will have a similar equation for hole diffusion current density. Just the difference will be we will have a minus sign in front that will denote that hole diffusion current density is in the negative direction. The constant here is dP. dP is the hole diffusion coefficient. So let's talk about total diffusion current density. This will be J diff, and this will be a sum of JNX diff plus JPX diff. Essentially, we will put the values of JNX and JPX. This will be E multiplied by dN multiplied by ddx of n minus E multiplied by dP multiplied by ddx of n. So this was our total diffusion current density in the x direction. Now the total current density is a sum of total drift current density and total diffusion current density. As we are considering the x direction only, you will be familiar with this part. This is the drift current density in the x direction, E n mu n E x. Ex is because now we are considering the drift in the only x direction. So we are considering the electric field at only x direction, Ex instead of E. Same thing for this term. And we have also our diffusion current density, this term. This is in only x direction. But if we consider the whole semiconductor, we will have equation of J something like this. J is equal to E n mu n E plus EP mu P E. We obviously know this part. And then we have E dn delta n minus E dP delta P. So that is all about diffusion transport phenomena. In our next discussion, we will have some elaboration and derive some other equations related to diffusion phenomena. Till then, goodbye.